Welcome everyone to today's talk and the Design++ seminar series. My name is Daniela Griego and I'm happy to be your host today. It is also my special pleasure to welcome our guests today who are a part of Design++, Romana Rust and Michael Kraus. Before we start the talk today and I introduce the speakers, I will shortly provide some information about the seminar series itself. So we have information on our website, YouTube channel, and we will also distribute emails regarding upcoming talks. So as mentioned before, you can look at our YouTube channel for past talks, and you can find the information here. So at the moment, there are a number of professors from architecture, civil engineering, and computer science from ETH Zurich involved in Design++. And for operational purposes and running the day-to-day business, there's a core team of the three of us. So myself and Romana and Michael. So we take care of operating the center. Romana and Michael are responsible for the Immersive Design Lab and research and teaching activities. So we have a growing number of scientists and chairs and professorships associated to the center. So if you're interested in learning more and the future of AI and machine learning, extended reality, and AC, just reach out. We're happy to discuss. So here we are. I'd like to I'm very happy to introduce our speakers today. They will give a talk on Augmented Intelligence Concepts for Design and Architecture and Engineering. So I'll start with Romana. She is a computational architect and senior researcher at Gramazio Kohler Research here at ETH Zurich, and also within Design++. She is the co-lead of the Immersive Design Lab. This is a collaborative research space for research and teaching in the fields of extended reality and machine learning in architecture and construction. And Michael, he is a senior researcher. He is at the chair of concrete structures and bridge design and co-leader of the Immersive Design Lab of Design++ initiative at ETH Zurich. So he researches and teaches in the area of scientific machine learning and the built environment. And you can see that the two of them are in the IDL today and giving their talk. So without further ado, I would like to hand over the floor to you, Romana and Michael.
Thank you, Daniel, for that. Hello, everyone. Today our roles are swapped. I'm not your host, but presenting together with Romana about some of our recent research within Augmented Intelligence for Design in Architecture and Civil Engineering. Rather than providing in-depth insight into our various past and current projects, in today's talk, we want to stay a bit more bird view or high level and provide to you our thoughts on necessary concepts for augmenting the design process. We hope that after this talk, key points for incorporation of different kinds of intelligence as well as augmentation are more clear, and we can inspire you with our vision on convergence of artificial and human intelligence in the future of design in architecture and engineering. Let's jump into the presentation with a question. So what comes to your mind if you think of augmented intelligence for the built environment? Is it a robotic utopic or dystopic view? Is that a thing which is a human-guided tool for support? Will it enable a more innovative, circular, and efficient infrastructure? Or is it a tool for supervision and control? Is it a tool for fostering collaboration? Or is it more marketing than reality? I can imagine that there is a variety of impressions, expectations, and thoughts towards my questions in your head right now. But I think we all agree that we need research to provide a systematic yet agnostic concept or concepts for augmented intelligence for design in architecture and engineering.
So augmented intelligence is one of these buzzwords today. And in our talk, we want to dissect avenues for augmented intelligence for design in architecture and engineering, and look at each of those words individually. So we will start with intelligence and investigate human and artificial intelligence, simulation intelligence, and design intelligence. And then we look at the word augmentation and talk about augmented memory, augmented human, and augmented intuition. And then finally, we will talk about the convergence of these two with an outlook. So let's start with intelligence. Intelligence in general is the capacity of creating connections between notions. In biology or psychology, it is the ability to learn or understand or to deal with new situations. So in this slide, we colored certain words differently, which you will see throughout the talk. Here, the color red relates to words with a retrospective aspect. Green is prospective or predictive, and blue is evaluative. So intelligence is also the ability to apply knowledge, to manipulate one's environment, or to think abstractly as measured by objective criteria. Here, apply knowledge would be prospective or predictive, and measured by objective criteria would be evaluative. Intelligence is also the act of understanding, so comprehension.
I think everyone is familiar with the typical course of Paulson and McLeamy towards the impact of design changes along the different phases of a design project. Today, we spared you this graph and instead wanted to present to you our view on the impact of human as well as artificial intelligence towards the design of structures of the built environment. I think we all would agree that the complexity in the sense of demands towards the function of a building, together with the societal as well as owner expectation on usability, have increased over the course of the past millennia. In the future, designing or retrofitting a structure will be an ever more complex task, where we assume this exponential behavior as indicated by the red line. Now let's draw two other lines for the contribution to the total planning effort in design or detailing these objects of the built environment. The orange line here indicates the human contribution, while the blue line represents the artificial intelligence contribution. And we also indicated with this dashed line landmarks in the digitization of the design and planning process, where especially in the 80s and 90s, the computer was introduced to enable computer-aided design or CAD. And in the last decade, more and more AI algorithms were applied to certain tasks within these design processes. This is marked with design 1.0 to 3.0. And with 3.0, I mean the building information modeling or BIM. The upcoming design 4.0 will more heavily rely on incorporation of AI. And we see the change of seeing the singularity within this century as AI algorithms get even more powerful and data from different sources are available. As a conclusion, for us, it is to be expected that at some point in the future, the AI will take over more workload within this whole design process, which gives rise to ask three questions. How will this collaboration look like? What tasks can be conducted by the AI? And how do we ensure that AI does the right things? In order to establish an understanding where an AI can be applied in a sensible manner and how this is enabled, we need to go back to the definition of the learning problem of this AI. This consists basically of three components. One is the performance, here in blue. The other is the experience, E, here in red. And the third part is the task T, here in green. So the task T itself is how the AI should process the data, or an example of the data. For example, design a sustainable but elegant house. Then we need to measure how good the AI does the job with respect to given performance criteria. This is done by this performance measure P. And for example, we can use the standard least squares error for that. And finally, we need the experience, which is basically the data set or data which is at hand to train the data or make the AI learn something.
Good. So let's investigate the capabilities of each agent. As you well know, computers are good for data storage, computing power, and search, whereas humans are good for general knowledge, perception, creativity, and experience. There are some capabilities that lie in between those two, that would be planning, diagnosis, prediction, and logic. Or, as in the words of Albert Einstein, computers are incredibly fast, accurate, and stupid. Humans are incredibly slow, inaccurate, and brilliant. Together, they are powerful beyond imagination.
Now let's take a cartoon as a funny resemblance of asking these important questions on the combination of human and artificial intelligence. So let's assume we have the situation shown on the very left. We are in the middle of designing an object and gathered some data on that. Before follow-up situations should arise, we need to have concepts for data gathering and proper analysis of that. We will shed some light on that in the next sections. The cartoon now displays three situations departing from these initial situations. So we have a good situation. Here, we should ask about the human in the loop. Here we need concepts for that, and this will be discussed, as we said, later in this talk. Then we have the situation bad. Here, adding AI basically augments data with mathematical models for description, and some pitfalls may arise. We will present to you a section on simulation intelligence and cover all that up. And then there might arise a situation which is marked here very bad. This means that we are having an AI algorithm mimicking the data generation process, and this is in general a very good thing. Yet, different AI architectures have their obstacles, and biases have big influences. In our section on design intelligence, we will discuss that a little bit. Now, let's turn our attention to data, which was the third part of the cartoon. AI is an inherently data-driven technology. This means that data is the fundament of any application of AI. But when looking at the data sets from the AEC domain, so architecture, engineering, and construction, we see quite a heterogeneity towards geometry, semantic, and quantity. For example, I brought to you this Fusion 360 gallery data by Autodesk with engineering objects on the left-hand side, or on the right-hand side, you will see some floor plans which consist or make up a data set. In general, what we will see is that AEC datasets share the four following properties. They're usually not enough, they're usually not diverse, mostly incomplete, and inconsistent in quality and format. A major concept for handling data in AEC is about imbalancedness. Diverse strategies of machine and deep learning exist, and this is, for example, using a stratified sampling method. But there exist other approaches, such as resampling the data or even acquiring new data in the AEC domain. And in many cases, that is connected to great efforts, and sometimes it's even prohibitive. So you cannot just gather more data in the AEC domain usually. As a summary, there is still research needed towards collection and processing of AEC data. For example, sensible data models such as the AFC format from BIM cannot directly be applied maybe to other situations, for example, in designing bridges. So far, this has been done neglecting the whole design process. Yet the data model of how we would store and describe the data has an influence on the representation of the learning problem. Besides the issues of the AEC datasets themselves, we have to be aware of another important entity, namely biases. Biases in AI occur when results cannot be generalized widely. We often think of biases resulting from preferences or exclusion in our dataset, but biases can also be introduced by how the data is obtained, which refers to the experience in the definition of the learning problems. Another bias can be introduced by how algorithms are designed. So this means a bias through the task T. And finally, a bias can be introduced and how AI outputs are interpreted. So here we would see a bias can also be introduced by the performance measure P. In general, if AI systems are biased, then so are their results. And this can benefit us, harm us, or benefit somebody else. Therefore, we should be aware of that. We can also show the introduction of biases within the training loop of an AI algorithm. We already have established that the bias is inherent in our training data, but can be also implied by how we would feed the data to the model. Another bias is introduced when we interpret the outcomes of that. And if you draw this as a circle, we will see that these different biases create a whole loop. Therefore, we already established it is important to have the human in the loop. We have to take care of these biases in the simulation intelligence and even in the design intelligence, which we will talk later about. Finally, to keep in mind, I think a major issue is that biases are rarely obvious. So think about your results from a search engine tuned to your preferences. We are already conditioned to expect that this will differ from somebody else's search on the same topic using the same search engine. But are these searches really tuned to our preferences or to somebody else's preferences, such as a vendor? The same applies across all systems. So if in the future we apply AI to design new homes, etc., we need to ensure that these biases, which are shown here on the slides, are understood and controlled in proper ways. So far, we handled issues concerning human or artificial intelligence and looked at the properties of AEC data and the role of biases. Now let's turn our focus towards simulation intelligence. When providing and preparing this talk, Romana and me came to the conclusion that most of you are familiar with work which is done in the community of researchers for applying different machine and deep learning algorithms for specific parts of designing a structure. Often the purpose of AI algorithms in design pipelines is to speed up or short-circuit lengthy numerical computations of performances. With that, I mean, for example, that we can train a machine learning algorithm to predict the amount of reinforcement of a column instead of running a nonlinear finite element analysis. This is especially handy in situations where the performance predictor model needs to be called several times during the design iterations. We decided to not show a bunch of examples where we applied standard machine learning and deep learning algorithms for design tasks. Instead, let me introduce to you two more novel aspects of AI algorithms for performance simulation tools, where we use biases to guide an AI algorithm, or we extract biases from data to inform our design decisions. First, let's turn our attention to the picture on the left-hand side. I put here a schematic of the promise versus reality of AI in simulation. The ideal world assumes that we have at hand big data, means a lot of data about our problem, and we are able to train the AI for correct predictions. We already established that AEC data suffers from different properties, which prevent them from being ideal for the AI training. In that case, an trained AI algorithm is biased and will have some problems for generalization towards other problems or unseen data. On the other hand, let's draw a picture for two other biases, namely data and domain theory. So we would draw here the use of data in that problem on the horizontal axis from low to high use of data. And on the vertical axis, we would draw incorporation of theory also from low to high. Now we might locate three distinct regions. The established scientific way of providing models of reality upon few data, but significant use of first principle knowledge, which is to the very left in this diagram. Another extreme is the standard or black box AI approach upon little theory bias, but huge utilization of data, which is on the lower part of the diagram. And the novel approach is blending theory and data, which you can find on the upper half of the diagram, which is marked here data-driven and theory-informed artificial intelligence. I myself have been active in the field of physics-informed deep learning for 2 years, and in the following I would like to present a first impression of that concept to you, as we can naturally now interpolate between those two extremes of black box and physics-based models. Given the limited amount of time, just let me explain the main building blocks of physics-informed networks, or PINs. Consider the situation: we need a performance simulator. For example, I want to compute the deflections of a membrane within the design of a football stadium. The classical approach here would be to set up a finite element computation for that. But now we would like to solve this task using physics-informed deep learning. First, we have as inputs the description of the problem, or also called features, which is in this case the spatial coordinates x and time t. We would feed that features into the neural network and obtain an output, which here is the deflection of the membrane U in the red circle. Now, in order to train and bias this training of the pins toward respecting physics, we need to provide in the governing equations and together with the boundary and initial conditions to state a proper problem. On the other hand, if we have at hand some data, for example, from finite element computations or measurements from the membrane, we could also feed it to the pins training, but we do not have to do that. So if you want to understand these two building blocks, I marked them here in red for the theory. So here we would take all domain knowledge from civil about this membrane bending problem. And as I said before, we could also introduce data, but we don't have to. This means we can naturally now interpolate between being purely data-driven. If we would leave out the theory, if we leave out the data, we would just be physics or theory-based modeling, and everything in between we could naturally handle with that concept. So after training this pin, we have ensured that this respects first principles via the governing equations, but have in addition the possibility to feed data to that process. And therefore, in my eyes, this has the potential for a real monolithic digital twin, as far as you would take the definition of that, at least for simulation twins. And yeah, this handles, I think, in a very nice, natural way, first principles together with data in the same computational framework. To give a small example, I give here an excerpt of the paper, which is marked on the right-hand side. We conducted a lot of experimental results on various tasks from civil engineering arising in the design of structures. Here, for example, we solved the Helmholtz equation for dynamically excited continua without bending stiffness. And you will see that the solution of the pin respects physics and has a very good approximation quality. Even NVIDIA took up our Relo-Bralo algorithm for proper weighting of the different losses here and implemented it in the last version of Modulus. Yeah, besides introducing biases in a controlled manner into the AI training, we may also want to extract biases for design. For that, I brought two examples for the extraction of biases for aesthetic perception with me. And one example is the work of my PhD student, Sophia Kuhn, and she works together with me on this aesthetic perception of conceptual bridge layouts. And the other work is currently conducted as a master thesis of Max Klaus and Lorenzo Lamarche on perception of architectural spaces, which is supervised Professor Dillenburger, Romana, and me. In both works, the idea is to conduct controlled experiments with distinctly designed structures. In the left case, it's bridges. In the right case, it's different kinds of rooms and hallways, and obtain a database towards the aesthetic perception by surveying a great number of people. What we want to establish in these lines of work is twofold. First, using an AI for finding correlation and structure within this data towards what drives people's aesthetic perception. And second, establish an AI-based performance predictor for aesthetics, which then can be used in the later stages of the design to inform decision makers.
Good. Now let's have a look at design intelligence. As you well know, the process of design starts by defining the problem, collecting information, goes over to brainstorm and analyzing, then develop a solution, feedback, then refine and remove, and then again redefine the problem. And that is based on the information and knowledge we gathered during iterating over this cycle and then start again. As you well know, this is a highly iterative process and well known as the wicked problem, as Riddle and Weber coined it, that is very much in contrast to any optimization problem. So far, we looked at simulation intelligence that can be maybe associated to those 2 points in the design feedback circle, whereas design intelligence may fit to these 4 parts here. Good. Now for design intelligence, it is also necessary to respond to sustainability. So there is 3 sustainability strategies that we should take care of. The first one is efficiency. So the efficiency strategy is technically oriented and aims to relative improvement, so doing things better. Here, for example, is the aim to reduce required material or energy input costs, etc. The next strategy is the consistency strategy. So in contrast to the efficiency strategy, consistency strategy aims at the maximum effectiveness, so doing things different. This means focusing on material flows, develop new material systems for fabrication, or renewable energy. It can be seen as an example for the consistency approach. And the concept of a circular economy is also closely related with this sustainability strategy. So the last strategy is the sufficiency strategy that can be seen as complementary to those 2. The aim of a sufficiency strategy is to encourage non-consumption behaviors, so doing less. And this is, of course, the most difficult one because it requires a behavioral change of consumers and industry actors. So if we want to use AI in architecture and civil engineering, the necessary components are hardware, software, and data, with contained patterns or hidden complicated mathematics. For machine learning, we obviously need methods from computer science and math and statistics. But how can we judge whether or not the data is useful or whether or not the found patterns make sense? And this is exactly where scientific machine learning comes into play as emerging disciplines within the data science community. So scientific machine learning develops new methods based on domain-specific challenges and extract insights from scientific data sets. Scientific machine learning draws on tools from both machine learning and scientific computing to develop new methods for scalable, domain-aware, robust, reliable, and interpretable learning and data analysis. The outcome of this combination are reference databases and metrics KPIs, linking back to the color scheme, what we introduced in the beginning, where reference databases would be retrospective, whereas the metrics and KPIs would be predictive and evaluative. The next big topic we want to introduce is augmentation. So augmentation is very much about interfaces. So augmentation means to increase something. Linking it back to the color scheme. So it means by making something greater or by adding to it, increasing it. In psychology, that means increase the amplitude of average evoked potential, either above background noise or by more than one would be expected from the increase in the stimulus. Human augmented artificial intelligence. So in this part, we investigate how the human is augmented, because every machine learning system is anyway always augmented by human bias, what we already talked about in the beginning. Let's take a look again at our circle, feedback circle of our design process. Augmented memory can be used in the step of collecting information. Augmented intuition or augmented creativity appears in that part where design thinking is augmented. So where a partnership between an AI and a human occurs, where unexpected design solutions may appear, which helps definitely in refining and improving the design problem. Augmented human then appears at many parts of this process, which is mainly augmenting one's capability to see and hear, which will be augmented by digital means.
So let's turn our attention to concepts for augmenting the human memory by AI. In the beginning of the presentation, we already outlined the properties of AEC datasets. In addition to existing datasets, a lot of information currently is not stored at all. For example, I read that in architecture, only 10% is built of what is ever conceived or planned in a digital world. So two questions arise. How do we store developed knowledge about design problems, and how to retrieve data and learn from existing buildings? To that end, the building of data sets is key, and concepts for creation, storage, and feeding to AI pipelines is necessary. To that end, let's look at the information update according to good old Bayes. You remember maybe him and his formula from school, where we take prior information and combine this prior information, which is given here by the probability of task A. We update this by the likelihood of P of B given A, and divide it by the evidence, which is given here as P of B. So we have then an updated posterior information about A and B according to that mathematical formula. If we now would tie this back to our legend and the three parts which we introduced in the definition of intelligence, we will see that the prior is acting as a retrospective element. We would see that the likelihood is used to be evaluative. And in the end, with the posterior, we would have a prospective or a predictive element seen here again. In order to fill this maybe abstract formula with a bit more life from the AEC, I brought to you an example of my research, which is the Bridge Genome Data Project. This provides a concept for augmenting future design processes with prior knowledge stored in existing building. We need to shift away from these silo working environments by building databases, which then enable AI algorithms to capture this implicit knowledge and provide it as a bias in the form of a prior within the design process. This is quite different from a data-driven process, as the prior is one part of the design process, which can be totally altered within the follow-up processes, as we have seen in the physics-informed networks.
The next part is Augmented Human. So here you see a collection of videos that use either augmented reality or virtual reality to augment the human. In this case, mainly the third dimension is used to convey certain information. For example, in the case of showing structural engineering content, or in a building detail, which is developed by one of our master students, or in the case of visualizing data. In this case, what you see in the upper right corner, this is measured acoustic data. Now, this is an example for data visualization that falls under the same umbrella. Here you see a self-organizing map on acoustic surfaces that have a certain acoustic performance, but are also evaluated based on their fabricability. Now imagine by adding a third dimension to this, it would of course improve to evaluate not only the performance, but also aesthetic considerations. And then also think about analyzing and viewing or discovering that space that is created by the self-organizing map in 3D in a VR setting. The last investigation here is intuition, so augmented intuition. In an augmented intuition setting, and the AI operator operates as a partner assisting in design space exploration. This is the case in a generative design and performance pipeline where a large amount of data is generated and one seeks to explore this design space. Here, for example, moving along the fitness surface and detect both performative and aesthetically pleasing designs. Another example for augmented intuition is this project here, Semiramis, an interdisciplinary project developed at the chair of Gramazio Kohler Research with many partners, amongst them the Swiss Data Science Center. As a sub-project, we developed a direct pipeline from the machine learned model to a render engine, in this case using Omniverse. You see here that a request for a design instance that has certain performance values is sent and then directly visualized, not as an abstract design instance, but fully rendered with materials, and in this case, trees. This would, of course, help in the early design phase if you discuss the design with many stakeholders in the team.
Today, we want to dissect what avenues for augmented intelligence for design in architecture and engineering are there to be investigated in the convergence. Therefore, we want to pose some questions. How can we create real benefits by embedding human cognitive skills into digital processes? And vice versa, by augmenting the human decision-making process with machine intelligence. So far, we have established that each of the players, the computer and the artificial intelligence, as well as the human and the human intelligence, have their pros and cons and are good for solving different problems in different situations. What we can do now is we can span two axes for the incorporation of the different actors in that game, so to say. For that, we can span from a fully automatic way of collaboration where just the computer and the artificial intelligence is solving a job, to the other extreme where just the human with its human intelligence solves in a fully manual way a certain design problem. And in between, we can think of a variety of different collaboration forms, which reaches from a computer in the loop where the main workload is still conducted by the human to the mixed initiative mode where the workload is shared equally, to the other extreme where the human is in the loop and the computer is doing, together with the AI, most of the workload. For that, we have come back to this established workflow of a generative design, and we propose to make that a mixed initiative systems generative design pipeline. Because what we would need is that we have to incorporate, on the one hand, AI and scientific machine learning as outlined. This can be done, for example, by augmenting the memory via databases, archives, standards. On the other hand, we can here augment the processes of generation, analysis, ranking, and evolving with what we called augmented intuition in order to create and get in these processes. And on the other hand, we need these human-machine interfaces. For example, with the Augmented Human, using extended reality technologies in the explore phase or in the representation phase on the end of the input data. So I think our vision of the future of designing AEC is this convergence of intelligences, and for us it is this multi-modal mixed initiative systems.
We are very visually overloaded, but actually humans are multisensory in nature, a fact that Morten Heilig already in the 1950s explored for theater. He developed Sensorama, a mechanical device which includes a stereoscopic color display, fans, odor emitter, stereo sound system, and emotional chair. This was actually the first multisensory virtual reality apparatus. Technology is moving more and more closer to us. It's becoming wearable. It started with the smartphone that we carry around in our pocket. We have AirPods in our ears and a watch that has a direct connection to our computer in the pocket tracking, for example, our movement. Additionally, our computers are starting to speak with us the same way as they communicate with other humans. So digital and physical worlds are overlapping one another. Keyword metaverse. This development will just continue. Not only we will have environments that allow us to easily talk to computers, but also the multisensory nature of the human will be utilized where we are actually interfacing to cognitive science. This video is from a colleague of mine, Daniela Mitterberger, where not only the direction of view is tracked, but also the size of the pupil that increases based on stimuli. While an AI is good in understanding multi-dimensions, we humans perceive and understand our environment through multiple sensors, not just the eye. And for a future augmented intelligence system, we need multisensory and multimodal interfaces. And with this futuristic thoughts, we would like to close this talk and look forward to the discussion. Thank you.
Thank you.
Right, so far from Romana and me. I think we had an interesting talk and a super cool discussion. As I said before, I will upload the information of this talk together with the video on our YouTube homepage. Eventually, I want to highlight our next talk on the topic of digitization for circularity by Professor Katrin de Wolf, which is already next Tuesday, 5th of April at 4 p.m. So thanks again for watching this video, being with us. Stay safe and see you next time.